Hello everyone, welcome to this presentation. I'm Kent and I'm here to share with you some insights about IoT security and device onboarding using a PUF-based device identity solution. So let me begin with my presentation. And first, let me quickly introduce myself and my company. PUFsecurity is a company dedicated on developing integrated security IPs, which, as mentioned as our name, most of them are PUF-based solutions. And I'm Kent, the PUF expert in our R&D team, and I've been working on PUFs for quite some years, so I'm here to share with you some latest research results on PUF and PUF-based solutions, and of course, what kind of applications they have. So let me begin with my presentation by illustrating some well-known security considerations in IoT. So, as you know, IoT is a complex ecosystem which involves in many layers. So all of them, they have different kind of security threats and what kind of solutions that they need. We need for all these different layers. So as for the endpoint devices, we typically care about the confidentiality of the information stored in these devices, and we also want to make sure that the device can operate correctly. For example, not booting with a malicious firmware or executing malicious programs. So again, then move on to the connectivity layer. The security communication between the network entities is very important. And in addition, remote control and remote updates of these IoT devices should be done also securely. And move on to the cloud layers. We want then to prevent malicious access to network services and or our databases. And of course, recently, because the number of the devices need to be connected in the cloud is actually increasing quite rapidly. So now how to efficiently and securely onboard IoT devices to the cloud has become quite an important topic as well. So then we take a look on the security considerations. So for all of them, many of security solutions has been proposed to solve these kind of potential issues. And of course, there are some basic requirements to enable these solutions. And we know that one of them, this requirement, is that all the devices or other network entities has to be securely identified. So next, I will introduce an example using a device onboarding to illustrate what is the role of the device identification. As you may already know, that FIDO has announced a specification for the IoT device on board, and in this scheme, we have seen that device identification has plays an important role. So, as specified in this FIDO specification, two of the main protocols, including the TO1 protocol and the TO2 protocol, the device needs to be securely identified, so it means that the device has to prove its identity. So in this scheme, the IoT device consists of a device attestation key stored in its restricted operating environment. And the device attestation key itself is actually a private key, which is strictly kept in this device. And there is also a public counterpart of this key, which is typically included in the ownership voucher. And as a part of these, we know it's called, sometimes we call this kind of publicly known device identity. So having these device attestation key and the public and the corresponding So having these device attestation key and the public key that's stored in the ownership voucher, we can do the onboarding. So while onboarding, the rendezvous servers and owner would like to know the device's identity to retrieve the device's public identity, basically the key from the ownership voucher. but they do not know actually if the device they are communicating is actually the legitimate owner of that public identity. So therefore, in above TO1 and TO2 protocols, the device will sign the challenges sent from the owner or the rendezvous server and send its signature back as the proof. So this signature can be verified using the public key, which is included in ownership voucher. And so the rendezvous server and the owner can verify if the device they are communicating is actually the owner of that identity. So afterwards, the onboard routine can be further executed. So we have seen an example showing how secure device identification scheme is supported by a unique key stored on the device. And now the important questions are, how do we get these keys? And how do we store this key securely? First, the key must not be easily predicted. So means that one cannot guess it out of nothing, or you cannot find any similarities to other existing keys. And or in shorter words, this key must be unique. So we want this key to be unique, the only key of this device. And in common practice, to make a key unique, the key needs to be go through a secure provision process. So it needs to be securely provisioned into the device and using some kind of dedicated setup. And secondly, this key must not be easily stolen by different type of attack techniques. So it is important that this key cannot be easily stolen, because if the keys are easily stolen, and no matter how the quality it has, how good it is, it provides basically no security. So it means that we cannot simply store these keys in a regular memory block without any protection. Instead, we should use a dedicated root of trust block to store this most important secret. And basically, these are the main role of having a root of trust. Speaking of root of trust, so we would like to know actually what is a root of trust. So in short word, it's a dedicated hardware to store and manage the most sensitive digital assets in our system on chip. And basically it provides security against attacks, and it can only be accessed by the crypto coprocessors to reduce the risk of the information leakage. After showing the need of the root of trust, I would like to give a few words on how do we implement it in silicon, and this also to show the position of our PUF-based device identity. So let me first refer to the OpenTitan root of trust. And as illustrated in the left-hand side figures, a root of trust in silicon involves designs and processes in different abstract layers, as illustrated in these two figures. And the right one, the OpenTitan project, they try to make these designs for root of trust as open sourced as possible. And if you are interested in OpenTitan, there is a presentation in Authenticate Conference 2020, which introduced this OpenTitan root of trust. So you can refer to that. And back to our design. So we basically acknowledge that moving towards open source is the right direction in terms of security and trust. However, due to the inherent limitation of the chip manufacturing flow, it is infeasible to make all the designs open sourced, and it is particularly difficult for the analog IPs or the embedded memory blocks to be open sourced, because these designs usually need to be finely tuned before and after manufacturing, making it quite difficult to maintain an open source version that can be easily adopted by the general public. Moreover, how to select and use pure analog IPs is difficult for most of the digital designers or system architects, how to integrate and how to choose the analog IP to be integrated with their digital parts could be a headache for many of them. So for this reason, we want to provide a plug-and-play solution for this ecosystem, which combines the hard and soft macro into an integrated security IP. And by doing so, it can be easily placed in an SoC design to provide this required security functions. So here we show the PUF-based device identity solution, or the device, the DID solution, as the right-hand side. It consists of a PUF, a true random generator, and a one-time programmable secure storage. It's OTP block. And in addition, there is an anti-tamper design equipped to make the root of trust more resilient to attacks. So the crypto engine is also placed aside to support the standard cryptographic algorithms, and this crypto engine also directly manages the assets stored in the hardware root of trust in order to make it more user-friendly and more secure. So if you have seen that PUF as a part of our root of trust solution, now I would like to introduce you what actually a PUF is. So the full name is physically unclonable function, and it provides a functionality like our fingerprints, and is therefore often called as the hardware fingerprint or a chip fingerprint. And a PUF should have the basic property listed here, or sometimes we can say the other way around. If you design a circuit that have all these properties, then you have already designed a PUF. And with the PUF implemented in our chip, we have enabled fingerprint within all chips that can uniquely represent the device's identity. And given these PUF properties, we can be sure that none of these device IDs can be blank, or this device ID, they cannot be cloned by anyone. So with all of these nice properties, I will later on show you how to use a PUF in practice. As I have illustrated this example of device identification in FIDO, a public key pair is the core component of the device identity. And this requirement basically brings up the most common application of PUF, which is the key generation. So in this simplified flow, a PUF is used to derive a set of secret data, and using this secret generated by PUF and sometimes combined with some auxiliary information, a public key pair can be derived. So the public key will be safely sent out for registration, while the private key, they must be strictly kept inside the chip. And the public device ID is typically registered and maintained by utilizing the conventional public key infrastructure or other alternatives. And the private key is used to sign messages in order to prove that the device is the legitimate owner of its identity. And this type of identification scheme is secure only if the device is the only entity that can possess the correct private key. So it is very important to make sure that the secret data generated by PUF will never be sent out outside the security boundary, and of course ideally it should be only accessed by the crypto engine to derive the key. Okay, so here I would illustrate some advantage of PUF solutions over the conventional ones. So first, let's take a look at the left-hand side. So conventionally, the SoC has an embedded memory block for key storage. So if one wants to provision a key into an SoC, a dedicated environment and equipment are needed to accomplish this key injection task, either owning the setup of itself in-house or buying the service from an industrial partner. But the cost of performing this key injection basically means that the cost of performing key injection is not negligible. And moreover, since the keys will be sent out to be programmed into the chip, there is always some chance of having it leaked or stolen in this process. So even though people tried very hard to make the probability can become very low, but there is still some kind of tiny chance that the key would get leaked or stolen, so we could not overlook this risk. And there is also a popular alternative, so is to replace the key injection. So instead of using the key injection process, we can also put a standalone secure element chip besides our SoC. So by issuing the key generation comment to the secure element chip, the correct key can be securely generated and kept within the secure element. And the secure element usually can also support signing and other different type of secured operations. So the private key doesn't need to leave the secure elements, making sure that it will not be accessed by any untrusted party, and it's also achieved the required high security. But of course, there is an obvious drawback. You can see that because we need an additional hardware, additional chip to do this key management and key provisioning. So basically add more cost to this entire solution. So as a result, we can see that having an inborn keys in the SoCs is the most secure and cost-efficient solutions, and which is comparing to the other two conventional methods. So we can see there how using a PUF-based device identity solution is quite beneficial. So as I've mentioned, the advantages of using PUFs. Now let's take a look at an example of what a PUF is, and of course what a good PUF is. So NeoPUF is a PUF based on a quantum tunneling mechanism. The basic bit cells consists of two NMOS transistors placed in parallel, and before using it as a PUF, it must be first enrolled, which is done by applying a high voltage stress on the gate oxide of the two transistors. And after the enrollment step, one of the transistors will be performed with a conduction path caused by the tunneling mechanism, and the bit cell and the enrollment process is designed to let the stress release as soon as a tunneling path is formed. So that makes sure that only one tunneling path is existing in either the left transistor or the right transistor. And having this result, we can define the two different cases as ones and the other one as 0. And these values can be read from sensing the current flowing through, flowing through each bit cell. And with a PUF array constructed by these bit cells, a secret data pattern can be derived as shown in the right-hand figure, and it can be used to derive the key pair for our PUF-based device identity. And the most important feature of this quantum tunneling PUF is that it achieves the state-of-the-art performance, including 100% stability without any bit error rate, and it's also insensitive to environment fluctuations, including voltage and temperature, and also it's resilient to aging, so there's no aging effect of this NeoPUF. And besides this state-of-the-art robustness performance, it's also achieved the ideal randomness and uniqueness. And to have all these advantages, it needs no additional processing steps, and also it needs no additional helper data algorithms. Another important feature of PUF is that it's resilient to reverse engineering. So like other non-volatile memory, the secret of PUF is stored in a physics form and stays within the chip, even if it's not powered. So given this fact, the attacker may try to obtain the secret data through reverse engineering by applying similar techniques that were used to attack non-volatile memories. So as an example shown here, if we use a conventional e-fuse to store the key, what can happen is that the zeros and ones can be clearly distinguished from the image obtained using the scanning electron microscope. And so you can see an open circuit and a short circuit in different on an unprogrammed fuse or a programmed fuse. And on the other hand, the data generated by a confidentiality PUF, if we apply the same technique on the confidentiality PUF, we do not see the same result, because if you see this this SEM image of our confidentiality PUF, the cell that is not not programmed and the cell it is programmed, they do not show any difference, so you cannot know the PUF value or the key values by doing reverse engineering on the confidentiality PUF chips. After showing the advantage of having a PUF-based device ID, now let's move back to the example of the FIDO device on board. So now we have this PUF-based DID embedded in our device, and we can easily use it to derive the PUF-based device decision key that can be used to sign challenges in both the TO1 and TO2 protocols. And the public key generated by using this PUF is also can be registered and then included in the ownership voucher to support these FIDO device on board specification. So basically, using a PUF-based DID, we can support the FIDO pretty well. So after illustrating its role in FIDO, I would like to move to the entire IoT ecosystem. So here we've roughly divided into 4 different sections, starting from the supply chain. Once a chip is manufactured, we already wanted to have the ability to be securely identified. So this is important for against adversarial supply chain activities such as a device counterfeiting and overproduction. And later on, after the device is being assembled and as a final product, the zero-touch device on board, which we've already discussed, would place its role. And having an inborn attestation key pair is quite important to support these onboard procedures, and it would have also other benefits in the IoT network management. Since we have shown the role of the DID in device on board and IoT network, now let's take a closer look on the supply chain side. And counterfeit has been a long-lasting issue in supply chain. And the first is about chip counterfeit. So here, an attacker may steal your chip design using reverse engineering technique, and within the stolen design, they can possibly reproduce a counterfeit chip that has exactly the same functionality. But if a DID is embedded in original design, because the PUF is resilient to reverse engineering, so it is no longer possible to reproduce the counterfeit chip that are exactly the same as the genuine one, because of course all the PUFs are unique and they are unclonable. So after solving the chip counterfeiting problem, let's move on to take a look at the case for device counterfeiting. So in this case, assume you are a device designer and you probably purchase some off-the-shelf components to assemble your device, and you have put most efforts to develop the firmware which powers up this device. And in this case, if you program your firmware in a non-volatile memory, there is a risk of the firmware being copied or stolen by an attacker, and this attacker can try to get all the thin off-the-shelf components and build the chip, and then program the firmware into the counterfeit device and make it work as the original one. So the solution here is that we can embed a DID in the SoC chip, and in this case we can encrypt the firmware using the device EID key, and then while the firmware is going to be used, it will need to be decrypted using the same key. So in this case, if the firmware is stolen again, since it is encrypted using the device EID key, the counterfeit device cannot decrypt it because it will not have the same key as the original device, so makes the counterfeit device does not work in this case. So we have basically solved the device counterfeit problem. The last supply chain issue I want to address here is about overproduction. As a device maker may request a chip maker to produce chips that are customized for a particular set of devices. The number of the produced chips needs to be well controlled. Otherwise, there may be an overproduced chip that goes into the gray market and falls into the hand of the competitors and to power their others' product. So the main concept of this solution against overproduction is to enforce that all the chip needs to be activated for becoming functional, and the chip is not activated will not provide any functionality or only limited one. And through this process, one can easily control the number of activated chip to prevent the overproduced chip from powering others' product, because the overproduced ones will not be activated and therefore not working. So how do we implement this solution using the PUF-based device ID? So since the PUF-based IDs already exist in the chip, so we can generate the activation code that is uniquely bind to the ID, or that sometimes we call the fingerprint, and they can program it into the chip. And the activation code is uniquely paired to the PUF ID, and the chip can only be activated if the ID and the activation code actually matches each other, and this is basically according to some cryptographic verification. And the number of the activation code is strictly controlled, and therefore only a certain number of the chips will be activated, and there will not be the overproduced one will not be activated. So in our hand, since an overproduced chip is not subjected into a correct activation step, so they do not have the right activation code corresponding to the PUF-based ID. So this chip will not be activated, and they will be useless if they're exploited by any adversarial parties. And it should be noted that even if the activation code is cloned from an activated chip, because the PUF is different for every chip, a chip which has a cloned activation code will remain inactive. So basically, cloning an activation code is basically useless. So this solution basically helps us to prevent the chip overproduction issue. So after seeing the last example, now I will conclude this talk. I've shown that device identification is an essential requirement for IoT security, and an IoT device can be trusted only if it can prove its identity. So to enable many of the security functions, root of trust is required to store and protect the digital assets, and it is essentially the foundation of the IoT ecosystem. We have also seen that the role of PUF in root of trust, and have demonstrated that the quantum tunneling PUF provides a highly secure and robust device ID. It is also important that the proposed PUF-based solution has well support the FIDO device on board specification and many other security applications as well. So in summary, these PUF-based solutions has enabled a more secure IoT ecosystem. Thank you very much for your attention, and feel free to contact us if you have any questions. Thank you and goodbye.